All right, hi, welcome back. This video is coming to you live from the Kiner room. Very exciting. Okay, so we've been talking a little bit about anti-differentiation, which is also called integration. So I've been using those terms interchangeably. They mean the exact same thing. If you're integrating a function, that means that you are finding the antiderivative of that function. Up until now, things have been pretty straightforward. There's rules that are basically just the opposites of the rules that we learned when we were doing derivatives before. But now things are going to get a little bit tougher. The functions are not going to be as obvious to find the antiderivative of. And so the way that we're going to deal with such problems is we're going to use something very cool called u-Substitution. All right, so first let me just remind you what differentials are. We talked about this a little bit in class a while ago, maybe a few weeks back. And the idea is this. We suppose that u, actually I think before we supposed that y was equal to f of x, but now I'm going to use the letter u because, I don't know, use a cooler letter. Don't judge me. So we're going to suppose that u is equal to some function of x. Then the differential of u, this is the definition, the differential of u, which we denote by du, is given by the following formula. Du, the differential of u, is always equal to f prime of x times dx, and dx means the differential of x. So you'll remember, when we talked about this in class, if you divide both sides of this equation by dx, you get something like du dx equals f prime of x. And of course, du dx is just an alternative notation for the derivative, right? So if u equals f of x, then du dx is equal to f prime of x. So that's kind of an easy way to remember this. But it has a different meaning. We're not really meaning like we're dividing by dx. It means the derivative of. So here, this is kind of weird notation, but the differential of u is always going to be equal to the derivative of your function, f prime of x, times the differential of x. Oftentimes it's going to be really useful to rewrite this, to solve this equation for dx. And to do that, you just simply divide both sides by f prime of x. So the differential of x is always going to be the differential of u divided by f prime of x. Okay, I hope this makes sense. If not, rewind the video, watch it a few times. But this is really just, definitions of what these things mean. Okay, so let's get to it. In your textbook, if you're using a textbook, usually they just call this substitution. I like to call it u-Substitution because that's how I learned it, and it's awesome. But really all that this is it's the chain rule backwards. So we're flipping the chain rule around. So if you liked doing the chain rule before, where you had to find the derivative of the outside function and then multiply by the derivative of the inside function, this is just the same thing but backwards. So here's a typical problem. Here's a typical thing that I would ask you to find. We want to find the family of antiderivatives of this weird looking function. Okay, you'll notice that I could, if I wanted to, multiply this all out. I could raise that x squared minus 5x plus 3 to the 4th power. It would be like a super foiling thing that I would have to do, and I would get a really nasty long polynomial, which I would then have to multiply by 2x minus 5. I do not want to do that. That's way too much algebra. It's way too much work. It is possible to do that, but I don't want to. What you should notice here is we have something really nice going on. The first function that's in parentheses there, that x squared minus 5x plus 3, is pretty nice. The thing that's in the other set of parentheses, the 2x minus 5, you'll notice that that is the derivative of x squared minus 5x plus 3. This is awesome. This is just like a wonderful twist of fate that we happen to have a function and its derivative both appearing in what's called the integrand. It's appearing as the function that we want to find the antiderivative of. This is going to make our lives super easy. The way that we're going to deal with this is we're going to use u-Substitution. And so the way this works is you just let u be equal to some portion of your function. And the smart choice here is that I want u to be equal to x squared minus 5x plus 3. I want u to be equal to this thing inside of the first set of parentheses. Why? Well, because I've been doing these things for years and I know exactly what choice of u is going to work out for us. Also, I made this problem ahead of time. With practice, you too will be very good at picking which part of the function u should be. And we're going to be practicing a ton of these in class, so hopefully you'll be feeling really good about it by the end of the week. Okay, so if we let u equal x squared minus 5x plus 3, Then you remember we would need to calculate du, which is the differential of u, and du is always going to be f prime of x times dx. So I hope that this is making sense. So in all these problems, you write something like let u equal whatever you want u to be equal to. In this case, it's x squared minus 5x plus 3. And then you calculate du. So I always like you use the word let u, and then you write then du. You get to choose whatever you want u to be, but then du you have to calculate. There's only one answer for du. Du is the derivative of this function, x squared minus 5x plus 3. So that's 2x minus 5. And you always multiply by dx at the end. This is just how differentials work. Du is equal to 2x minus 5 times dx in this problem. Okay, hope everybody's with me so far. Let's continue. You'll notice now that we can substitute things in. So what this means is anywhere that you see an x squared minus 5x plus 3, which appears right here inside of the parentheses, I'm going to replace with u. So that x squared minus 5x plus 3, I'm going to substitute with a u instead. And then this 2x minus 5 dx, which appears right here, I'm going to replace with du. That's what du is equal to, right? So this becomes du. So when I substitute everything in, I hope you're seeing this okay, the integral sign is going to stay there, and then instead of having x squared minus 5x plus 3 raised to the fourth power, I'm just going to have u raised to the fourth power. And then instead of multiplying by 2x minus 5 dx, that is just equal to du. So I'm going to have u to the fourth times du. Technically this is times, but we don't need to put the time sign there. So when I substitute these values in, I get the integral of u to the fourth du. Okay, I hope that makes sense. That's a nice easy integral to calculate, because that's just the power rule, right? This is saying, in English, what is the family of antiderivatives of u to the fourth? And of course the answer is 1/5 u to the fifth plus c. That's just the power rule that we know and love. So you'll notice that at this step, I'm actually taking the antiderivative, and when you do when you find the family of antiderivatives, you don't include that s thing anymore, the integral sign. You don't include the du in your answer. You're just finding the family of antiderivatives. So my antiderivative of this function is 1/5 u to the fifth plus c. There's a little problem here that we have to be careful. My original function was a function of x, and if you tell me that the answer is something involving u, that's going to be a problem, because I want everything to be the same letters, right? If I start with x's, I want to end with x's. If I start with t's, I want to end with t's, and so on. So once you get to this point, don't forget to go back and substitute in what u was equal to. You remember that u was equal to x squared minus 5x plus 3. So that means I need to plug that in for u into my answer that I got here. Okay? When you do that, you get a very nice answer of 1/5 times the quantity x squared minus 5x plus 3 raised to the fifth power, then plus some arbitrary constant. Don't forget that plus c on the end, still important. Don't forget to check your answer by simply taking the derivative, and when you take the derivative, you're going to be using the chain rule. So that's why this is the chain rule backwards. So let's do this check together real fast. Let's check our work. So my original function, I'm going to call it f of x, is 1/5 times x squared minus 5x plus 3 raised to the fifth power. What is the derivative? Well, we have to use the chain rule, right? And so our outermost function is 1/5 times something to the fifth power, so we can take the derivative of that using the power rule for derivatives. You would get 5 times 1/5, which is 1, and then x squared minus 5x plus 3 goes down 1 power, so it becomes x squared minus 5x plus 3 to the fourth power. But then you have to remember to use the chain rule and multiply by the derivative of the inside function, which is 2x minus 5. And I believe that's exactly what we started with, folks. Nailed it. Fantastic. Always check your work, especially with these problems. I don't think we were checking our answers very much before because the integrals were easier to calculate. The antiderivatives were easier to calculate. Now things are a little tougher. So I highly recommend checking your work. Okay. Unfortunately, life is not always so easy. In that example, it was really nice because we had a function and its derivative both showing up inside of the integrand. You'll notice for these two problems that is not the case. I want you to try these out for homework. We'll talk about them in class. But for the first one, we should let this thing be equal to u. And for the second one, we should let the exponent be equal to u. I'll give you that hint at least. But what you'll see is that when you calculate du, you don't get what's left here. So for instance, up here when u is x squared plus 4x plus 5, if I let u equal x squared plus 4x plus 5, then du is the derivative of that, which is 2x plus 4 times dx. And unfortunately, I don't have a 2x plus 4 dx. I have a 4x plus 8 dx. So how are we going to get around that? A similar problem happens in the second one. So I want you to play with these a little bit, see what you can come up with, and we'll talk about it in class. All right, thanks for tuning in. See you soon.